There is friction between how lawyers write regulations and engineers build systems. The law relies on fluid interpretations. Engineering requires strict deterministic logic. Standard relational databases struggle with this translation. A table mapping users to email addresses does not natively capture the situational reality of why data was collected, where it is allowed to go, or who has the legal authority to process it. To bridge this gap, system architects need a standardized, machine-readable ontology. They require a structured vocabulary capable of explicitly defining the relationships between the what, how, where, who, and why of enterprise data workflows. Without a shared semantic bridge, mapping multi-jurisdictional compliance across complex data pipelines remains a manual, error-prone guessing game for engineering teams. The Data Privacy Vocabulary, or DPV, is a W3C-backed ontology designed to solve this translation problem, built on semantic web standards like RDFS and SCOS. It provides a universal format, turning abstract legal requirements into machine-readable classes any system can parse. We will map the DPV core architecture from first principles to understand how it binds isolated points of metadata into fully compliant process graphs. Implementing DPV takes legal compliance from a static, reactive paper document and turns it into a dynamic, deterministic graph structure living directly inside your code. At the center of this architecture is a single foundational node, DPV process. This is the core binding agent of the entire ontology. This concept replaces the deprecated version 1.0 personal data handling concept, aligning the model directly with standard enterprise software terminology for any action or activity. From this central process, we establish specific relationships. We trace the has data edge outward to define the exact categories of data being utilized. We trace the has purpose edge to document the precise justification and operational goal for touching that specific data. We trace the has legal basis edge to ground the operation in regulatory permission, whether explicit consent or legitimate interest. Finally, we trace the has entity and is implemented using technology edges to define responsible actors and the technical systems executing the workflow. By tethering everything to DPV process, the architecture acts as a definitive anchor. It prevents isolated metadata from floating out of context and creating unintended legal liabilities. Modern regulatory frameworks like the EU AI Act and the Data Governance Act strictly regulate enterprise operations that extend far beyond traditional personal data. This timeline comparison illustrates how DPV version 2.0 physically expands its core scope. Where version 1.0 built a boundary strictly around personal data, the new architecture encompasses broader nodes, including generic data, non-personal data, and technology. This allows the framework to seamlessly integrate new core extensions, such as DPV AI, directly into the existing graph. As a result, fundamental relations like has purpose are no longer restricted to privacy laws. They can now be used to legally justify the use of generic algorithmic training data alongside traditional personal identifiers. This architectural expansion unifies traditional data protection protocols and broad-scope AI risk management under a single interoperable graph structure. However, this scope expansion introduces a critical breaking change in taxonomy implementation that engineering teams must immediately account for. This taxonomy tree highlights the structural shift.
Previously, applications queried the data subject class. Now, dpv.humanSubject is the parent node, with data subject and the new tech.subject branching entirely beneath it. This reclassification is necessary to accurately capture humans who interact with AI technologies or act as subjects of a model, but who may not be explicitly sharing their personal data at that moment. Engineering teams must proactively update their application queries, UI dropdowns, and database inputs to target the new human subject class to avoid logic breaks in legacy systems. Adapting to these exact semantic shifts ensures your enterprise data schema remains legally accurate and structurally resilient against rapidly evolving AI legislation. Let's apply this to a complex real-world data supply chain. Consider the Acme pipeline. As a data controller, Acme collects user email addresses for two distinct reasons: internal service provision and third-party targeted marketing. This diagram shows what happens if you dump all of that disparate metadata into a single flat process node. You get a chaotic tangle of red, contradictory edges crossing between internal privacy permissions and external processor rules, creating invalid legal interpretations. The architectural solution to this supply chain chaos is the use of DPV nested processes. Instead of one messy block, we safely separate the business logic by physically splitting the master process into isolated, self-contained nested processes inside the main service wrapper. Process A now contains only the logic for the internal analysis purpose, tied explicitly to the strictly necessary core data points. Process B is entirely separate. It contains the specific third-party data processor entity, the external marketing purpose, and the distinct consent mechanisms required to legally execute that action. This nesting technique entirely eliminates data duplication. Because the processes are nested, they share the same base email asset while strictly siloing the legal responsibilities between internal and external actors. Nested processes provide the deterministic way to model modern, multi-layered data supply chains involving complex third-party subprocessors. Scaling up from a single nested process reveals the architecture of a comprehensive enterprise compliance graph. Tracing this taxonomy's depth, a path drops from a generic data processor down to a specific national authority, while another tracks a commercial purpose down to DPV targeted advertising. These granular taxonomies replace the vague text of a privacy policy with absolute, queryable, machine-readable definitions. This comprehensive mapping allows legal compliance teams and back-end engineering teams to finally communicate using the exact same structural language. The ultimate goal of the DPV ontology is integrating compliance logic directly into the enterprise stack. Possessing a unified, queryable graph natively enables the automation of mandatory data protection impact assessments and maintains real-time risk logs without human intervention. The framework establishes frictionless interoperability, allowing systems to pivot across global regulatory frameworks, mapping CCPA requirements over GDPR logic without requiring total database rebuilds. This ontology provides the strict, immovable, and definitive framework required to safely manage all sensitive enterprise information. By utilizing the data privacy vocabulary, organizations provide a mathematical proof of compliance at every single node in their architecture.